Good morning, everyone. My name is Sarah Parker, and I'm doing our presentation for assignment 2 for our machine learning class. For this assignment, um, the goal was to classify CFAR 100 images into 20 superclasses using a multi-layer perceptron. These images were already flattened with 3072 features. And then the method involved using a systematic grid search, which evaluated 64 permutations of hyperparameters like units, activation functions, and optimizers. Because this was such a large assignment, I won't be able to run through the entire program. It took me about 2 hours and 40 minutes to run it, but I am going to go ahead and start it so that once I'm kind of in the midst of my explanation, we'll be able to see some of the execution results here. Um, each um, each permutation takes about 3 to 4 minutes to run. So we'll come back to this part in just a second, but we'll go up to the top to kind of start walking through the code. So essentially, I have the two files, train and test, in this Google Drive folder. So in order to access it, but then make the code reproducible for our professor to see, I downloaded the direct URL and then used GDown. So when you do that, it actually downloads the files into your file manager during the Colab runtime environment for use in the analysis. So that was how I did the train and the test to import it into the PyTorch code. So from here, essentially the model is going to use 5 layers of a fully connected network. And then we used iter-tools, which is a function in Python that allows us to automate the 200 epochs of training, which is what we were asked to do, was 200 epochs. That was why it made it so long. But one of the trickiest parts, I think, that the instructions alluded to is that we have our hyperparameter dictionary here, but the when you have to pair the loss functions, the cross entropy loss needs raw logits, while the MSE needs an explicit output activation like sigmoid or softmax. And it likes to do softmax, so you have to specify that specifically. So for our model, we're using PyTorch. Additionally, I have it up here to run off of a GPU. I have it set for T4. Otherwise, if you use a CPU, it's going to take too long. So this is just kind of an extra little line of code to ensure that we're using a GPU if it's available. Otherwise, it probably was not going to run without having a timeout activation. So this is right here, the output layer activation function. So the cross entropy loss will automatically use the log softmax, but when we're using categorical cross entropy, we cannot do softmax. We have to pass those raw logits. So this is our code to make sure that that happens only if using the MSE loss function, if that gets selected during one of our permutations. Our optimizer is going to be either the atom or the eta grade. The loss function is cross entropy or the MSE. And then we label these. I do one hot encoding labels, which I believe is further up here. No, it's further down. Anyway, there is one hot code for the labels. Wish I could find that. Anyway, and then we're going to, when we run our model, we're going to run it for the 200 epochs, and then we're going to do our output, our loss, our optimizers, and then our batches, and then we're going to do our eval as well. Okay, so as it's going through the different permutations, utilizing the different hyperparameter combinations, this is how I did mine. So initially I had it saved to my Google Drive folder, but then I realized that if somebody else was running it, it would throw an error because it wouldn't be able to access that Google Drive. So if it's not in my Google Drive when I'm running it, then it's going to make an output directory here in the folders. So you can see the test and the train were downloaded, and then the grid search results are right here. So this is where our output is going to be saved. And as a safety, I went ahead and had it just update the CSV every time it completed one of the 64 combinations. That way, in case something went wrong, I would at least have some data to look at. Thankfully, that did not happen. I did not have a timeout, and I was able to run all 64 combinations. Like I said, it took about 2 hours and 40 minutes, but it did run it. But this is what I have printed to the console just so I would know that it was working. So for the first one, the parameter it used was 120 units. The hidden activation was ReLU, activation was softmax, loss was MSE, the optimizer was ADA, and our batch size was 1,000. And then it tells us what our accuracy was and our validation accuracy. So it's going to keep doing this. I'm going to go ahead and stop that for now because I already have the results saved from the last time. So I wanted to briefly go over the report that shows the results. So it took it from 100 fine grain categories into our 20 course superclasses. We didn't have to flatten it, like I said. The training set contained 50,000 samples and the testing set contained 10,000 samples. And then labels were one hot encoded, there it was, for the use with MSE loss, and kept as an integer indice for use with the cross entropy loss. So that was kind of the key for this assignment, was to make sure that the output was appropriate depending on the loss. Coming down here, so this is just a screenshot showing what that looked like, which I showed you as it was running, but that's just shows more examples of it. And then it was saved in a CSV. I then made a Python file to analyze those CSV results so that we could figure out exactly which ones were the best. And for my model, this was the top result, and it's ranked by the validation accuracy with the training accuracy. So you'll see the it's ranked from validation accuracy first and then training accuracy. So the top combination was using 240 units with a hidden activation of ReLU. Our output was sigmoid. Our loss was a cross entropy. The optimizer was an AdaGrad. The batch 1,000, and we got a 36.43% validation accuracy with a 54.5% training accuracy, which this is a figure just to kind of show the difference between the two. But I believe that ended up being, trying to do some quick math, like around 10%, 9% difference between the two. So that's pretty good. You start to see greater differences as you go further down. When it comes to analyzing the hyperparameters, for hidden activation, the top two were ReLU and sigmoid, with 29 for ReLU and then sigmoid for 19.5. That's a 10.3% difference. The loss activation, cross entropy did better. Output activation, softmax did better. The batch size, 1,000 did better. Units, these were really, really close, but 240 was a little better. And then the optimizer was pretty equal between AdaGrad and the Atom. So one of the important things to see was the degree of overfitting in the Atom optimized combinations. The most extreme case used Atom 240 units, ReLU, softmax, cross entropy with the batch size of 1,000. Which achieved a 99.8% training accuracy, but only a 34.1% validation accuracy. That's a 65.7% gap. That's huge. That definitely shows that Atom was overfitting all of that. So it just, the actual validation was much, much lower than what the training was. But the contrast to that was that the best performing model using AdaGrad had the training validation gap of only 18%, suggesting that AdaGrad's more conservative update behavior was better regularized. So it learned maybe less accurate but I would say more accurate because the validation gap was actually less. The failed combinations basically just produced random guessing because they were 8 of them and they produced about a 5% validation, which out of 20 classes, 1 out of 20 is 5%. So these were just random guesses basically. And that was ReLU, sigmoid, and MSE, and then sigmoid, sigmoid, and MSE. The impact of the hyperparameters I thought was very interesting. The hidden activations actually had the biggest impact at 10.37%. The optimizer, and secondly, the units, but had very little impact. The optimizer was pretty much negligible, and I would say the units were pretty much negligible. So that's important because if you're training your models and fine tuning, you can really focus in on the hidden activations. The hyperparameter that's going to impact your model the most. So you don't have to spend as much time worrying about the optimizer and the units because it just really didn't have that much impact. So this is just kind of difficulties and notes. My biggest difficulty was really just figuring out how to download the files and then save the new CSV file for use further. And then the challenging part, as I mentioned before, was the label formatting for the loss functions, just to make sure that we had integers, raw logits, and then the floating point one hot vectors. So this was the biggest part, is just to make sure that our loss was labeled appropriately and selected appropriately. I believe that is about it. So all 64 combinations were trained and logged. We had our best performing model achieving 36.43%. As expected, the accuracy was low. This was told to us in the assignment that the MLPs do really poorly on image data anyway. And this is primarily because they're processing each pixel independently. There's no aware of spatial relationships between neighboring pixels, which is very key for images to be able to see those relationships. So anyway, this was assignment 2 for machine learning on our multi-layer perceptron model. Thank you.